Hello, welcome to this lecture recap video, and we'll get started right away with a quick recap of what we talked about last time. And that was the fourth of our special types of gas processes that will often appear in various applications coming up. So we talked about a situation where heat doesn't flow in or out of the gas during the process. And this either could be because the walls of our cylinder are very well insulated, or because the process happens very quickly. And so the process happens maybe faster than the time scale for heat to flow out into the walls of the cylinder or the environment. Okay. So in either of these cases, we can say that Q is equal to 0, and we call this an adiabatic process. And so we did a demonstration last time of an adiabatic process where we rapidly compressed the gas in a cylinder, and we found that in this case, all of the work that we're doing is energy that's transferred to the gas molecules themselves, heating up the gas. And so we found that we could actually produce a dramatic increase in the temperature of a gas, and we were able to ignite a bit of cotton just from compressing a gas in a cylinder, just air in a cylinder compressed at about 15 times, and then the temperature was up above 700 Kelvin. Okay. So today, now that we've understood aspects of these four different processes, we're going to start putting things together and talking about interesting kinds of cyclical processes that happen in various useful technologies. So let me skip this for now. Let me give you an example of one of these cyclical processes that turns out to be useful. So there's something called a heat engine, which in general is a machine that involves a cyclic thermodynamic process where heat that we add to the system during the process is partly converted into work on the environment of the system that we can use for various means, such as making a car drive down the highway. So this particular cycle it's called the Stirling cycle, but it's just one example. And so the idea is here we've got a gas in a cylinder. There's a piston that can move up and down, and in this case we have a hot object, sort of a heat reservoir that we're maintaining at a high temperature, and a cooler object, so some heat reservoir that we're maintaining at a lower temperature. And so we'll be able to add energy or add heat to our gas with the hot reservoir, and sometimes energy will go from our gas into the cold reservoir. So let's have a look at what this cycle looks like. We start out with a heated gas, which is being kept at a small volume. At some point now, we release the piston, and so the gas is allowed to expand, and we see an increase in volume here. This happens slowly in this particular cycle, and so we can take the temperature of the gas to be the same as the temperature of the hot reservoir during this process. At some point, we then switch these gates, and so now the gas is insulated from the hot reservoir and exposed to the cold reservoir. Then what happens is that heat will leave the gas cools down. We're holding things at constant volume here. And then at some point, we will release the piston. So at constant volume, if the heat is leaving here, then the pressure in this gas will decrease. And so once we release the piston, then the outside pressure being greater will push the piston down. And so that looks like this. So now we get to this, again, small volume step. And this again is assumed to happen at constant temperature because we're in contact with this cold reservoir. Now we switch the barriers again. And so we're put in contact with the hot reservoir. Heat is allowed to flow into the cylinder. We keep it at constant volume, and so it heats up, increasing the pressure, and now we're ready to start again. When we release it, it will expand again. And so this is an example of a cyclic process where we could go around and around and just keep doing this. And the point of all of this is that if you analyze the work that's done by the gas in the various steps of this process, what you find is that there's a net positive amount of work done during the cycle. And it's easy to see from the graph because in number 4 and number 2, the volume is not changing. And so there's no work being done. Number 1, the volume is expanding. So there's positive work being done. That work is the area under this curve. For number 3, the work is negative, but in this case, the area under the curve is less than for number 1. And so the net work done by the cycle is going to be positive. It's actually the area of number 1 minus the area under number 3. So it's the area inside the cycle on the graph. So by doing this, what we're doing is supplying some heat to the gas. Some of that heat is expelled into the cold reservoir, but not all of it. So we have some of the heat that we add being converted into this mechanical energy, and that will allow us to do useful things. So that will actually allow us to move things or rotate things and so forth. Okay. And so what we're interested in is to analyze these kinds of processes. So what we might be interested in is how efficient is a cycle like that in converting the energy that we provide from the hot reservoir into work. So there's a precise definition of efficiency that we'll be dealing with, and that is how much heat did I add during the entire cycle? So that is just the sum of the positive Qs during the cycle. And you compare that to how much net work is done during the whole process. So W is just the sum of all the Ws for the entire cycle. And what we're computing is this ratio of the work W that the gas does, it's the sum of all the Ws, dividing it by the Q, which is the sum of all the positive Qs. And that's our definition of efficiency. Okay, and so the idea is to produce these positive Qs. That's where we're, say, burning some fuel or using some battery power or something to supply heat. And so we want to know, like, what percentage of that energy that we supply is actually coming out in useful form in actual mechanical work. Okay, the rest of it is basically wasted energy. It's expelled into the environment. And in our example, it was expelled into this cold reservoir. Okay, so before we get into some calculations of efficiency, let me just then remind you of the tools that we've now accumulated in order to perform these sorts of analyses. So just a quick summary here. There's only so many things that we're ever going to ask you to calculate, and we can kind of divide these things into two different categories. One category would be different types of energy. And the other category is the temperature, pressure, and volume of your gas at various points on the cycle. So usually you have to do this temperature, pressure, volume calculations first in order to be able to do your later calculations. And the formulas that you will use in order to identify the temperature, pressure, volume at various points will generally be either the ideal gas law, okay, for the constant temperature, volume, or pressure processes, then PV over T equals constant is very useful because then one of these variables is also constant. And so, for example, at constant volume, we conclude that pressure over temperature is constant. And so if there's a doubling of pressure, then you can deduce there's a doubling of temperature. Okay. So that's going to be your basic strategy for calculating temperatures, volumes, and pressures. There's one special case, which is the adiabatic case. That's where the pressure, volume, and temperature all change during the process. And in that case, it's less easy to directly use this PV over T equals constant. What you need to do is use these other formulas that we derived that have this Greek letter gamma, the ratio of Cp and Cp. Okay, so for adiabatic processes, if we want to calculate temperatures or pressures and how they're changing, then we can remember that temperature times volume to the power gamma minus 1 is a constant in an adiabatic process. And similarly, pressure times volume to the power gamma is a constant. And so those would, for example, allow you to figure out the change in temperature for a certain change in volume when you have an adiabatic process. Once you have all of those things, then you'll often be interested in calculating the various kinds of energy for processes. So for efficiency, we're going to need heat and work. And often what you'll do for these things is kind of think about so let's say you need to understand what heat is for a part of a process. So often it's going to be useful to write down the first law of thermodynamics and see what that tells you. Okay, so sometimes you'll also need to calculate delta U in order to calculate W or Q. And delta U is the simplest of these three things because you always calculate it in the same way. It's always this formula NCV delta T. You always use the C at constant volume for calculating delta U, regardless of what type of process it is. So delta U is a kind of universal formula there. Calculating W, in principle, it's always the same. It's the area under the PV curve. But then the way that you actually evaluate that is different in different situations. So if pressure is constant, then we could simply use the formula P delta V, which was our original definition of W. Otherwise, I think one other formula that you need to just remember that it exists is the one for constant temperature. And so this is where the curve is like a 1 over x curve. To calculate the work, you need to find the area under that. We don't have to do integration every time. Basically, we just need to do it once. And we realize that the result of calculating the area is this formula with nRT log of V final over V initial. So those are kind of the two formulas that you'll need to remember for work. And then all of the other situations, so calculating work for an adiabatic process or calculating heat in any of the cases, then the thing to do is just refer to the first law of thermodynamics. So my advice is anytime you're stuck where it's not obvious what formula you should use, write down that first law of thermodynamics and then see if you can use that in order to calculate the thing that you're stuck on. Okay, so we're going to do tons of examples today. And so hopefully all of that will be a little bit more clear after the examples in today's lecture. Okay, so instead of analyzing this particular cycle and calculating its efficiency, what I wanted to do is analyze a slightly different cycle that is what we use to kind of approximate what's going on in an actual internal combustion engine. So your standard engine in a gasoline-powered car is going to be is going to be driven by the following cycle that, let me actually, okay, so rewind a little bit. I actually forgot we had a question. So in fact, we are going to look at this Stirling cycle a little bit first in this clicker question. Okay, so then we'll talk about the internal combustion engine, and that'll be a slightly different cycle. But let's actually do this one first. So this is the one that I showed you where you have constant volume processes and constant temperature processes. And so I wanted you to actually just think about in this cycle, how many of the processes have a positive Q? Okay. So that was important for calculating efficiency because we're only going to add up the Qs that are positive. So pause the video for a moment here and think about that question of how many of these processes will have a positive Q and therefore contribute to the Q in or QH that we use in calculating efficiency. Okay, let me find my preferred pen color, which today is going to be something called cerulene. Cerulene. It's an interesting pen color. Okay, so this is the blue I'll be using. let's think about the answer to this question. So what we'll do is actually think about each of these processes, and we're going to ask ourselves, is Q positive or negative for each one of these processes? And so my hint was that it's always going to be useful for us to think about what the first law of thermodynamics tells us. So we can rewrite that as Q equals delta U plus W. And so now let's start with process number 4. Okay, so process number 4 is constant volume. And the thing to remember there is that W is going to be equal to 0 because work is only done when volume changes. So therefore, Q is equal to delta U. Delta U is always equal to N CV delta T. And then we just have to ask, in process 4, is temperature increasing or is it decreasing? And this is a situation where we see pressure is increasing. So it's a constant volume process where pressure is increasing. And so we know that temperature should be increasing because remember, pressure over temperature is, so since pressure over temperature is constant for a constant volume process, right? So this is like our constant volume gas thermometer. Pressure is proportional to temperature. So we see that increase in pressure means there's an increase in temperature. Okay. And so that means, so finally we conclude that Q is equal to delta U is equal to NCV delta T, which is greater than 0. So for process 4, Q is greater than 0. In a similar way, we could say that for process 1, again, Q is equal to delta U, and that is going to be less than 0 because in this one, pressure is decreasing at constant volume, and so temperature is decreasing, and so delta U is negative. What about process 1 and process 3? So first step, ask ourselves what type of process is process 1? It says isothermal, so that means constant temperature. Again, we can refer to the first law of thermodynamics in order to calculate Q. And so we could remember that delta U is proportional to the change in temperature, and so it's 0 in the case of constant temperature. Okay, so delta U equals 0, and so Q is equal to W. And so for this process 1, we see that volume is increasing because, and therefore work is greater than 0. So whenever volume is increasing, work is greater than 0, and so we say our Q is positive. For process 3, then again, Q equals W, but it's less than 0 because volume is decreasing. Okay, so Q greater than 0 here, Q less than 0 here. And so in the end, we have 2 out of the 4 processes where the heat is actually flowing into the gas, where Q is positive. And if we were calculating the efficiency of this cycle, we would then add the Q for number 4 to the Q for number 1, and we would just ignore the other Qs in our calculation of efficiency. Okay, so now finally we get to the internal combustion engine. And so let me show you a quick video introducing this internal combustion engine. And I found a fun video from who knows when, maybe the 60s, or actually probably earlier than that. It's in black and white. Oops, there it is. Some of it was in black and white. No, this is actually in color. So maybe 60s. This is from the National Film Board of Canada. And here we go.
The internal combustion engine. The engine works in 4 stages. First, a valve opens and the piston lowers, letting a mixture of fuel and air into the combustion chamber. Second, as it comes up, the piston compresses the fuel-air mixture. Third, a spark from the spark plug ignites the mixture, which pushes the piston down again. Fourth, the exhaust valve opens, and as it comes up, the piston pushes the spent gases out. And the cycle starts over again. Intake, compression, combustion, exhaust. Intake, compression, combustion, exhaust. Intake, compression, combustion, exhaust. The movement of the engine is transmitted to the wheels for the driver's delight.
Okay, so there we go. Back to my slides here. So I'm going to break that down. Oh, I think we've still got a video going. Thank you. Google autoplay. One moment. Let's close that guy. How do I get rid of this thing? There we go. Okay. So let's break it down. So we saw a video showing kind of a cartoon version of the inside of a gasoline engine in a car. And what you noticed is that in the engine, there's several of these cylinders, and these are literally metal cylinders. There's a piston that moves up and down. There's air inside the piston. And in this internal combustion engine, we actually send the fuel in to mix with the air during the cycle. And so our starting point here is a point in the cycle when we've added some gasoline into some mist of gasoline into the air in our cylinder. And then the first step after we've done that is to compress the air and the gasoline. So the engine is operating very quickly. The piston is moving up and down rapidly. And so we approximate this compression here as an adiabatic compression step. Okay, so that's the first thing that happens. We're compressing the air and the fuel. It's adiabatic. And so we expect that to heat up a lot. The pressure is going to increase a lot. At that point, what we do is actually ignite the fuel. This is the job of the spark plug in your car. Okay, and so for a standard gasoline engine, we have this spark that is timed to fire as the piston reaches the top. And that will then start this chemical reaction where the gasoline burns. It's exothermic, and so a bunch of heat is released into the cylinder, into the cylinder. Oh, I should come back here so you can actually see me. So there's a bunch of heat that's released, and this happens very rapidly. And so we approximate this to be something that happens at constant volume. The piston's at the top, the spark fires, the gasoline releases all its heat. The added heat increases the temperature, it increases the pressure a lot. And so we move up here on our diagram. Now, at this point, so the extra pressure is going to push the piston down with a lot of force. And so we have this step, which again happens very rapidly. And we model this, therefore, as an adiabatic expansion of the gas. Okay, so this is called the power stroke. That's really where the power, this is where our gas is doing the most work. Well, it's the place where the gas is really doing all of the work, the positive work during the cycle. And so that pushes the piston down. It's connected to this thing, which I believe is called a crankshaft. So the linear motion of the piston is converted into some rotational motion of your axle. And so then the next step is to kind of replace that exhausted fuel with fresh fuel. Okay. And so in an actual engine, that happens through another motion of the piston up and down. So in the actual engine, what happens is that the crankshaft is still turning, and so that forces the piston back up, and we open this exhaust valve to force the exhaust out of that tube. And then it's timed so that when the piston is coming back down again, the intake valve is open, and so that sucks in some of additional gasoline. And so at that point, we're back to our original situation where we have air mixed with gasoline. Okay. And so the actual process now on the PV diagram involves this extra decrease in volume and increase in volume. During that process, we don't really add any heat, and the work is very similar, very close to zero. So the work is the positive work that we get in this first step is very similar, that's negative work. It's very similar in magnitude to the positive work that we get in the second step. Okay. And so what we often do is just approximate this entire process by simply a straight line that goes down from here to here. Okay, so the actual engine cycle is, we call it a 4-stroke engine. So bigger, smaller, bigger, smaller. But in our analysis of this internal combustion engine cycle, what we do is approximate that last step as just a constant volume cooling, where we're replacing the burned fuel and air, which is going to be hotter. We're sending that out, and we're sucking in some new gasoline and air, which is going to be cooler. And so overall, we could say during that process, it's to a good approximation for the purposes of calculating efficiency, just something where you jump from one temperature and pressure to a lower temperature and pressure at that constant volume. Okay, so this is the cycle that we're actually going to analyze, just this 4-step cycle. The idealized version that I just described is called the Otto cycle. It's not AUTO, it's OTTO, just as a coincidence that it has to do with cars. It's named after a physicist named Otto. And so when we're talking about the Otto cycle, you should think of that as like an idealized version of the cycle that happens in a real internal combustion engine. So our goal for the rest of the lecture is going to be to calculate the efficiency of this internal combustion engine. So this is a very standard kind of problem that you'll see in homework and midterms and exams. You'll be given some kind of engine cycle. Sometimes they'll draw a graph like this. Sometimes they'll just describe the different steps in the process, and you'll have to draw the picture. So either way, you will want to calculate the efficiency by figuring out the work and dividing by the heat. But I'm going to guide you through this step by step. And so what we'll do is solve the question. I think it's in basically 4 steps. So these are the steps that you are going to take when doing questions like this in tutorial homework exams, and it'll always be very similar. Okay, so step 1 is often to figure out what the temperature and volume and pressure is at the various points on the cycle. So usually you're given some information, some of those volumes or temperatures, and then you have to use the equations that we have to figure out the other volumes and temperatures and pressures, because those will come into our calculations of the work and the heat. So let's consider this cycle. So in this case, what we're given is the temperature at A, maybe that's the ordinary air temperature, and we're given that the compression ratio of the engine, that is the ratio between the largest volume and the smallest volume, is equal to R, little letter R. Maybe it's 10 in a real situation, or 8. We're also given this ratio between the pressure at B and the pressure at C. Okay, so we are given some information about the cycle, but what we'll need later is to know what the various temperatures at B, C, and D are in terms of the temperature A. So that's what I'm asking you to do now. Figure out the temperature at B, C, and D in terms of the temperature at A. So pause the video and see if you can use the equations from before to work out those various temperatures. Okay, so let's have a look. And so let's start by looking at the process A to B. Okay, so the process A to B is adiabatic. And we go from V max to a volume V min, and we want to find this temperature. And so when we're dealing with adiabatic processes, that's the situation where you're going to use these special formulas with the gamma. So we remember that T times V to the gamma is a constant. And so in practice, the way we use that is to say that T times V to the gamma at the final step, at the final configuration, is equal to T times V to the gamma at the initial configuration. And so we can rearrange that in this situation to give that TB is equal to TA times VA over VB to the gamma minus 1. And this thing right there is our compression ratio. So VA is V max, VB is V min. And so we can actually simplify that to say that the answer is TA times our compression ratio R to the gamma minus 1, okay, where we recall that gamma is defined to be Cp over Cv. Next, we have the process B to C. This one is constant volume. So for all the other ones, other than adiabatic, then it's usually most convenient to work with the ideal gas law equation that PV over T is a constant. And so in the constant volume case, what we know is that then P over T is also a constant. So pressure is proportional to temperature. And so then we can say that TB over TA, or sorry, TC over TB is equal to PC over PB, which is defined to be X in the statement of the problem. And so what we conclude is that TC is equal to TB times X. And if we want to write that in terms of TA, we use that TB is TA times R to the gamma minus 1. So we get TC equals TA times R to the gamma minus 1 times X. So it's a little bit complicated, but that's the way it is. Next, we've got our final process from C to D. And this one is also adiabatic. In this case, instead of a compression, it's an expansion. And so we expect our temperature to decrease. But the method is going to be the same as we did in the first step. So we can say that TD is equal to TC times, and then in this case, we'll end up finding, so if you follow the same steps as above, we're going to find a 1 over R to the gamma minus 1 because we've got the expansion rather than the compression. And so plugging all that in, using our previous result here, then we find that TD is equal to TA times X. Okay, so we have all of those things. We're going to use them later, so I will set this aside. Those temperatures are going to be useful in calculating the work and the heat that we need to calculate the efficiency. So step 2 is that we're going to calculate the net work for this whole cycle. And so we can start with, say, the process B to C. And so very quickly, I want you to just think about what could we say about the work for the process from B to C. So take a moment to figure out what we could say about that, answer A, B, or C. Okay, so hopefully you've paused it, thought about it, and are committed to one of these answers. So the correct answer here is that the work for process B to C is equal to 0. And that's because V to C is a constant volume process. And we remember that work is something that is positive for increasing volume, negative for decreasing volume, and it's 0 for volumes that stay the same. That comes from our basic formula that the work is equal to P delta V. So in order to calculate the net work for the cycle, we only need to worry about the work from C to D and the work from A to B. And that's our next question. So pause the video and see if you can figure out what the work is from C to D in terms of the number of moles, CV, and the various temperatures that we've calculated and the volumes and the pressures. Okay. And so the tricky part here is that it's an adiabatic process, so it's a curvy line, and we don't actually have a formula for work for an adiabatic process that I've derived. But there's actually another way to figure out the work, which is much simpler. Okay, so let's work it out. And the trick here is to remember that whenever we're stuck on something, if we don't have a formula for the thing we're trying to calculate, then it's always useful to refer back to the first law of thermodynamics. So we have that delta U equals Q minus W. And so for an adiabatic process, we have that Q is equal to 0. And so if I want to calculate the work, then it's just equal to minus delta U. And so in the process C to D, then the work is equal to minus N CV delta T, which is TD minus TC. Okay. And similarly, if we want to calculate the work from A to B, then we could say that work equals minus N CV and then TB minus TA. So we've got our work for all of the different processes. We can now add those works up. And what we find is that the total work, the net work, it's the sum of all the works, including the positive ones and the negative ones. And that's equal to N CV. And now I'm just going to combine everything, just making sure that I get the right signs for everything. So the TA comes with a positive sign because we got a minus and a minus. TB is negative, TC is positive, and TD is negative. Okay, and that's just what we have there. Finally, we need to calculate the heat, specifically for the processes where heat is positive. And so we can first ask the question, how many of these steps have Q greater than 0? So take a minute to think about that while you pause the video, and then we'll discuss it. Okay, so what we know is that for the adiabatic processes, then Q is equal to 0. And so actually we only have to worry about the process B to C and the process D to A. So those are constant volume. And in that case, we know that W equals 0. And we know therefore that Q is equal to delta U. And so it's positive for this process B to C, and it's negative for the process from D to A. And so we only have, in this case, one of the steps where the heat is positive, and that's the process from B to C. And so for our efficiency calculation, we only need to calculate one heat. That's the process from B to C. And so that's our next question. This is the last thing we're going to need to calculate in order to evaluate the efficiency. So to do it, we basically just use the formula that we had here. So to calculate the heat for constant volume, since work is equal to 0, Q is equal to delta U, and that's equal to NCV delta T. In this case, delta T is the final temperature Tc minus the initial temperature Tb for our process. And that's the last thing that we're going to need now. Okay. So let's now finish our calculation of efficiency. So we have that work is equal to NCV times this combination of temperatures. Heat going in, so this is the Q in, that's NCV times Tc minus Tb. And so the efficiency, W over Q in, is equal to Tc minus Td plus Ta minus Tb over Tc minus Tb. Okay, so let's actually work that out. This is when we're going to use our previous calculations for the temperatures. So let me summarize everything we learned. So we found all of the temperatures in terms of Ta. And so I'm just copying out our results from that previous slide, that Tb equals R to the gamma minus 1 Ta, Tc equals R to the gamma minus 1 times X times Ta, and Td is equal to X times Ta. So now let's calculate our ratio, W over Q in, which we found for this process to be Tc minus Td plus Ta minus Tb, over Tc minus Tb. And so that, plugging everything in from above, is R to the gamma minus 1x. So actually what I'm going to do is factor out. So basically all of those have a factor of Ta. So I'll just put Ta outside of everything. So we get R to the gamma minus 1x times Ta for Tc. Td is then minus x. Ta, we'll just have a 1 there, and Tb, a minus R to the gamma minus 1. And then on the bottom, we have Tc minus Tb. So that's going to be R to the gamma minus 1x. Again, I'll factor out the Ta, and then minus Tb, which is R to the gamma minus 1. Okay, and so I can cancel off those TAs. And now I'm going to try to simplify the remaining thing. So what I'll do is on the top, I'll sort of separate this out. We notice that 2 of the terms have an R to the gamma minus 1. So I can factor that out. And then the other 2 terms I'll write as x minus 1. And then on the bottom, I have an R to the gamma minus 1 times x minus 1 if I factor that. And so now all of this simplifies down. So you see the first term here is just 1. So it's this guy over this guy. Those are the same. And so our first term in this expression we can say is 1. And the second term, it's minus x minus 1 over x minus 1 times R to the gamma minus 1. So it's actually just minus 1 over R to the gamma minus 1. So we actually get this very simple final result that the efficiency for this specific cycle, for the Otto cycle, which is our approximation to what's going on in an internal combustion engine, what we find is that the efficiency really only depends on the compression ratio. So that was the ratio between the max volume and the min volume. The bigger that is the more compression we have, the more efficient our cycle is going to be. And so that informs the design of our car engines. So we want to design our car engines with a large compression ratio in order to get a high efficiency. But there are limitations to that we'll talk about next time. And so I'll postpone that discussion to the beginning of next class. And so that'll be it for today. And Friday, we're going to talk a little bit. We'll summarize that. We'll talk about the constraints on the compression ratio. We'll talk about the difference between this engine and a diesel engine. And we'll talk about the other kind of useful machine we can get, which is a refrigerator. So all of that's coming up on Friday.